Hey guys, this is the answer key to exercise set 1.5. Okay, so 263 is we have a graph to the right and we're identifying limits and outputs of different values. So first one here, limit of f of x as x approaches negative infinity means we're going to look at the function and approach negative infinity. So as we're going to a negative infinity, what is our function? What is our y value approaching? And we can see here it is approaching, it's got this like horizontal asymptote at 3, which means as I go to negative infinity, the limit is going to 3. Okay, now look at positive infinity. So as I'm going to positive infinity, going this way, what's happening to my output or y value? It's going down, right? It's going to keep going down forever, which means we are going towards negative infinity. Okay, f of negative 2. This is not a limit. This is asking what is the output of the function at negative 2. So we're going to go, so this is negative 1, negative 2. We're going to go to negative 2. And I'm going to ask, okay, what does my function equal at negative 2? Well, you have kind of two options here. I'm going to zoom in so you can see. We have this filled hole here, and we have an open hole. Remember, the open hole it's getting very, very close, but not touching. But the filled hole is where it equals that value. So this is f of negative 2, which is 1. Okay, so f of negative 2 equals 1. Now, the limit as x approaches negative 2. To do this, we instead of looking at what the function equals, we are approaching negative 2 from the right side and from the left side. So as I approach negative 2, look, I'm getting closer to negative 2 here. Okay, I'm going towards negative 2. What does my function approach? My function actually approaches 2. So even though f of negative 2 is 1, the function approaches 2, which means the limit is 2. Okay. Next, f of 0. So when I plug in 0 into the function, what do I get? You might be tempted to say, oh, you get infinity, but that's incorrect. When I plug in 0, there is no value here, right? We have essentially a horizontal asymptote going up here. It's never going to touch this. So it's not 0. It's undefined. Okay? Undefined. Okay? As x approaches 0, what is the limit? So this is a different question. So if we look as we approach 0, right, we're going towards 0 here. What is happening to the y, my output? It's going straight up on both sides. It's going to infinity. The limit is infinity. Okay. F of 3. 1, 2, 3. At 3 right here, what's the value of my function? Why don't you guys go ahead and, if you haven't answered this yet, what is the output of the function? Okay. See, this is an open hole. See, this is a closed hole. It's kind of hard to see on my screen, but on your paper you should see. Since this is the closed hole, this is f of 3, which is at 4. Okay. F of 3 is 4. Limit as x approaches 3. So we'll go back, we go to 3. We're going to approach it from both sides. So we approach it from the right, and we approach it from the left. Notice the limit from the right is 4. We approach 4. Or sorry, 3. The limit from the right is 3. The limit from the left is 4. So since they're different, the limit does not exist. Is the function continuous at x equals 0? No, it's not continuous at x equals 0 because f of 0 is undefined. No, f of 0 is undefined. Okay, we're going to talk about continuity in 74 as well, 274. So here we're looking at the graph to the right, and we're identifying 4 values where there's a discontinuity. That part is easy, right? And each of these values state the conditions of continuity that fails. So first, just visually, where are we breaking continuity? We should all be able to get this, right? So we're breaking continuity here at x equals negative 2. This is called a removable discontinuity. Vocab term, discontinuity. Because you can sort of see, it's like we've taken a hole and drawn it somewhere else. So it's like we've removed a point that's removable. This right here is a discontinuity at x equals 0. This is called infinite discontinuity. It's basically, this is a vertical asymptote. Here we have a discontinuity at x equals 1. This is called a jump. And then we have another one at x equals 2. We have a hole. Okay, so removable, infinite, jump, and hole. Now we need to state the conditions of continuity that it fails. So reminder, the conditions are as follows. You need to know these, you need to memorize these. 1, 2, 3. Number 1, simply the limit exists. Okay, that means limit as x approaches a from the left of the function equals limit as x approaches a from the right. So the limit from left and right are equal. That's number 1. Number 2, f of a is defined. So remember, in our first problem, we said that f of 0 is undefined because there is no output. So basically, there needs to be an output. That's what number 2 is saying. And number 3, the output needs to equal the limit. You need to memorize these, okay? You need to know these 3. So if we look at the first one, what rule are we breaking? Well, okay, let me write a kind of table out here. So we're going to have x equals -2. That's our first point here. And we're going to go through the checklist. So does the limit exist? Well, when I approach it from the left and the right, it's the same. It's approaching 1.7 or something, it looks like. So the 1 is good, all right? 2, is it defined? Yes, it is defined because f of -2 is 1. So it's defined. I'm going to do this. I'm going to say 1, check, is fine. 2, check, it's defined. How about 3? Does the output equal the limit? No. See here, the output is 1. The limit is 1.7. So it fails 3 because f of -2 does not equal the limit of the function as x approaches -2. The limit, and I'll sort of right above here, the limit looks like it's about 1.7. And then the output looks like it's about 1. So these are not equal. That makes sense? So limit exists because it's the same from both left and right. The output exists at 1, but since the output does not equal the limit, it fails. Okay, I'll go through the rest. So it's -2, but 0. So does the limit from the left equal from the limit from the right? Well, at 0, limit from the left is -infinity. Limit from the right is +infinity. So it fails number 1. Fails. They don't equal. Number 2, is it defined? No, it's not defined. There's no value at 2, so it's not undefined. And then 3, since it failed 1 and 2, it's not defined, and there's a limit, it fails 3 as well. It fails all 3. Okay, so again, check mark is pass, x is fail. Okay. Next one, x equals 1. Number 1 is the limit. Does the limit exist at 1? So does the limit from the left equal the limit from the right? If you have not done this by yourself, I want you to do this one by yourself. Does the limit from the left equal the limit from the right? As I approach 1, do they equal? Yes or no? No, right? Limit from the left is about 1. Limit from the right is 2. So it fails number 1. 2, is it defined? Yes, it is defined because we have a solid dot right here. So it passes number 2. And then 3, does the defined value equal the limit? No, because the limit does not exist, right? So this one, the problem is the limit does not exist. Limit from the left does not equal limit from the right. And then last one is x equals 2. Again, if you have not done one of these by yourself, do it by yourself now. We're going to look at 2. Number 1, does a limit from the left equal the limit from the right? Does the limit exist? Yes or no? Yes, it does, because the limit from the left is around 1.5, limit from the right is 1.5. So that does pass. 2, is it defined? Is f of x defined at 2? Does f of 2 exist? Yes or no? No. We have a hole. It's undefined at that point. Not defined. And then 3, because it's undefined, can it equal the limit? No. Okay. All right. 249. So this is just translating it into a sentence. Like, what is this saying in a sentence? So what this is saying in a sentence is, as x approaches, what are we approaching? -1 from the right. Remember that plus means -1 from the right. That plus means from the right. And then you would say your function, which is x plus 1, square root of x plus 1 plus 3, approaches 3. That's all it's saying. As x approaches -1 from the right, the function square root of x plus 1 plus 3 approaches 3. That's it. For b, again, so this is conceptual, right? As time approaches infinity, the soda's temperature approaches room temperature. That's all it's saying. Okay. Next one. I think we have time in this recording. I'll probably add another recording to this one and merge them together so that I can take my time. Yeah, I'm going to do that. So I'm going to pause it here, and then I'm just going to add another video. Okay. Picking up where I left off, we're at 252. Write as many limit statements as you can about the function graph below as x approaches -1. Remember, this means approach. This little arrow means approach. As we get closer to -1 and as we approach positive negative infinity. So let's start with -1. So again, visually, we look at -1 right here. I want to write as many limit statements as I can. So we know I can write 3 limit statements about -1. I can write what is the limit as x approaches -1 from the left. I can write what is the limit as x approaches -1 from the right. And then, the f of x comes after all these. F of x comes after all these. And then I can write the limit overall. What's just the limit as x approaches -1 of f of x. Okay? So let's go through these. Limit as we approach -1 from the left. We're going to approach it from the left, draw my line. As we approach it from the left, we get to a -1/2. Be careful with the scale. It's not -1, it's -1/2. That's -1/2. Okay? As I approach -1 from the left, my output or my y approaches -1/2. As I approach, again, if you get that, try the rest by yourself. As I approach from the right, my output or my y approaches +1/2. This is from the right. This is from the left. That's +1/2. Okay, and so the limit overall, remember, since these two values are different, the limit overall does not exist, DNE. Okay. Positive and negative infinity. So with positive and negative infinity, there's no approaching from the right or the left, right? Because you can't approach positive infinity from the right. It's easier in a way because it's only one limit you have to worry about. Limit as x approaches positive infinity of f of x, and then limit as x approaches negative infinity of f of x. So let's take a look. As we approach positive infinity, look visually, right? What is from the on the right side? As we approach positive infinity, my output looks like it's approaching 0. As I approach negative infinity, same thing. What is my y value approaching? So I'm going to say just for visual, this is positive infinity, this is negative infinity. As my x approaches negative infinity, it looks like my y is approaching 0 as well. So you should have 5 limits for 252. Okay. All right, last question, 71. So we have a function x minus 3 over x plus 5, and we're evaluating the limit as we get to infinity, negative infinity, as well as negative 5 and f of x minus 5. So first one, as we approach infinity. Now we're going to go over this on Wednesday, the 21st, but I'm going to go over this in the video so you can get a head start. So when x is approaching infinity or negative infinity, what we're really talking about are horizontal asymptotes. Okay, so if you remember from earlier in the unit when we learned about horizontal asymptotes, to find where they are, we're looking at the degree of the function. Okay, what is the behavior as these x values get really big? So when I say degree, if you remember, degree is the highest exponent. Remember, degree equals highest exponent. So all I care about here really is the x's. The 3 and the negative 5. If you imagine when you get to infinity, those are irrelevant. So what I have really is x over x, right? Now, since the degree is the same, this degree equals 1, this degree equals 1, there is a horizontal asymptote at 1 over 1 or 1. Let me kind of show you this in another way. So you can imagine this as like, this is a really, really big number over a really, really big number. And when you have just a massive big number over the same massive big number, you get 1. Okay, you can think about it that way. And we'll go over some other examples of this next class. Same for negative infinity. So you just care about the x's because the negative 3 and plus 5 are irrelevant. You have x over x, same degree. So you have the same horizontal asymptote at the you divide them, right? You divide their coefficients. And you can think the same way. You have a negative really, really big number over the same negative really big number. And that is, again, 1. Basically, essentially, like negative infinity over negative infinity. Infinity over infinity equals 1. Okay. Now let's look at limit as x approaches negative 5. So as we get towards negative 5, notice when I showed you limits at the beginning, I talked about you just plug it in. What is this function doing as we get close to negative 5? Well, when I plug in negative 5, you're going to get an undefined value. You're going to get 0 in the denominator. So it's hard to tell from here. But what you can do, one way to tell the limit is by plugging in values very, very close to negative 5. So let me show you an example of that. So I'm going to make some space. I'm going to bring C down here. Okay. So what you could do is plug in negative 4.9 and negative 4.99. And obviously, like, we don't know what negative 5 is. And then you could plug in on the other side negative 5.01 and negative 5.1. And what that will tell us is what we're approaching. That's what I'm doing here. So this is my x right here, and this is my f of x. So when I plug it in here, it's going to tell me what we're approaching as we get to negative 5. So I'll plug in negative 4.9. I'm just doing it in my calculator over here, so you know I'm doing negative 4.9 minus 3 that's negative 7.9 divided by negative 4.9 plus 5, and I get negative 79. Okay, and I'm going to plug it in again for negative 4.99 minus 3 divided by negative 4.99 plus 5. I get negative 799. Okay, so we can see visually here, we're getting bigger, we're getting more negative. Looks like we're going towards negative infinity. Let's plug in negative 5.1. So again, negative 5.1 minus 3 divided by negative 5.1 plus 5 is 81. And then negative 5.01, negative 5.01 minus 3 divided by negative 5.01 plus 5 is 801. So based on this trend, right, we see negative 79, negative 799. Remember, we don't know what this is. This is a question mark, if that's unclear. And from the other side, we're getting 81, 801. So we're going up to positive infinity, and the other side, we're going to negative infinity. So I can see from this, the limit is not going to exist, DNE. Why is that? Because I can see from this table, limit as x approaches negative 5 from the left. That's down here, right? We're going from negative 5, negative 5.01, negative 5. That is positive infinity. And the limit as x approaches negative 5 from the right is negative infinity. And I'm going to show you that on the graphing calculator. So you can also graph this online, but on a graphing calculator, you would go to y equals, you can see this okay, and you would plug in that function, x plus 3 over x plus 5. Make sure that's right. Or x minus 3. Right, x minus 3 over x plus 5. You graph it, and I know it's kind of hard to see here, but you can see this is negative 5 right here. This where the asymptote is, and as I approach from the right, I'm getting to negative infinity, and as I approach the left, it gets to positive infinity. Visually, something like this, where this is negative 5. Okay, so that's why the limit does not exist at negative 5. Okay, the last one here, D, f of x minus 5, that just means plug in x minus 5 into the equation. So what we'd have is, instead of x, we'd have x minus 5 minus 3 over x minus 5 plus 5. And that's going to be x minus 8 over x. That's D. And that's exercise set 1.5.